in this video we're going to talk about oxidizing alcohols, and the simplest way of oxidizing alcohols is just to burn them, just the combustion reaction, and yet that's not the way of oxidizing that we're going to study in this video here. We're going to use an oxidizing agent to oxidize alcohols, and we're going to get some interesting new products that we'll look at in detail. Just a point about the backdrop here. Backdrop of nail varnish remover would be one of the products that you get when you oxidize a certain type of alcohol. So when we're studying this topic, oxidizing alcohols, here's a few things that we're going to cover. We need to learn about aldehydes, ketones, and carboxylic acids you probably know about. These are the products of the oxidization reaction that we're going to look at. So we need to define each of those three products, look at their functional groups, etc. Then we're going to look at specifically the oxidation of primary alcohols, which is different to the oxidation of secondary alcohols, which is different again to the oxidation of tertiary alcohols. And finally, we need to be aware of the tests for aldehydes and ketones. Okay, so let's start off with getting our heads around what aldehydes, ketones, carboxylic acids are. We can do that using a table such as this one. So starting off with aldehydes, why not? Let's start off with the general formula of an aldehyde. General formula of an aldehyde is CN H2N O, and we'll see why the O is left separate like that when we draw an aldehyde. Let's draw an aldehyde. We've got this is what we're going to call the alpha carbon, because this is the carbon that's attached to our carbonyl group, and on the other side of the carbonyl group in an aldehyde is a hydrogen, and on the other side of the carbonyl carbon in an aldehyde is an alkyl group. Let's just call it R for now. So that's the general formula and displayed formula of an aldehyde. Let's have a look at some examples. Let's draw propanol. And the first thing to notice about the name is the ending, propanol, as in aldehydes, and the prop is going to give us the length of the main carbon chain. So MEP, so we're going to have 3 carbon atoms. So let's draw a carbon chain with 3 carbon atoms. Now it's an aldehyde, so the carbonyl carbon has got to be attached to a hydrogen. So we know that the carbonyl group is going to come off carbon number 1, and then the rest are just hydrogen bonds like so. So we've gone from a diagram from a name to a diagram. Let's do it the other way around. Let's draw a molecule and then name it. Let's draw an aldehyde molecule and name it. Okay, so let's say we've got a CH3 group attached like this to a carbon chain. Let's have another CH3 group down here, and let's have the carbonyl carbon on the end, like so. Okay, so let's work out the name of this one. So first of all, we want to check out the functional group. So we can see the functional group is here, and we know that we've got a hydrogen hanging off the carbonyl carbon, and the carbonyl carbon is obviously linked to a double bond oxygen, so we know it's an aldehyde from that functional group. Then we're going to number our carbons. There's number 1, number 2, number 3, and actually this might as well be a straight one because there's number 4. So it's going to be based on butanol. So let's can we write it? Let's write it down here. So it's going to be something butanol, but it's not just straight butanol, because we've got this methyl group here that we've not accounted for yet, and that's hanging off the second carbon. So we're going to call this one 2 methyl butanol, and that's how we would name that aldehyde there. Okay, so we can move on now to ketones, and the general formula for ketones is just the same, so let's write that out. But the functional group of a ketone is slightly different. We still have the carbonyl carbon, like so. So this bit is similar to an aldehyde, and yet with a ketone we have alkyl groups on both sides of the carbonyl carbon. And these alkyl groups can be anything, but they're not hydrogens. If one of them was a hydrogen, it would be an aldehyde. But now that we've got two alkyl groups on either side of that carbonyl carbon, it is a ketone. So let's draw a ketone. Let's draw propanone. And notice again about the name that the ending of a ketone is ONE, just like in the ONE of ketone. So when we draw propanone again is 3 carbons long, so let's draw a 3 carbon chain. So in this case though, our carbonyl group is not going to be on the end because we need 2 R groups on the end. The only option for the carbonyl group is go on the middle carbon like so, because we need an alkyl group, in this case a methyl that I'm just drawing on the right. And because it's propanone, we've got another methyl on the left-hand side. Okay, and so that's propanone. As we did with the aldehydes, let's draw a molecule, then name it. So let's say we've got 5 carbon chain, shall we? There's a 5 carbon chain. Let's make it unsymmetrical. So we're going to put our carbonyl group just there, and I won't draw all the H's in for the hydrogens. You know they're on the end of all these bonds. Okay, so let's name this one. So we're going to number the carbons first, and what we want to do is we want to number them from the end that makes the carbonyl group have the lowest number, right? So that would entail numbering from the right. So that would be a 1, 2, 3, 4, 5. So we've numbered the carbon. Now we've got no methyl groups or anything to worry about. So it's just we just have to illustrate where the carbonyl group comes in the carbon chain. You can see it's on carbon number 2. So the name of this ketone is going to be pentan because of 5 carbons, 2 because the carbonyl group is on carbon number 2, and one because it's a ketone. Okay, so that's pentan from 5 carbons. That's 2-one because our carbonyl group is on the number 2 carbon. So there we have the basics of ketones. Let's move on to carboxylic acids, and the general formula for carboxylic acids is CnH2n+1, and then we need to put the OH group, the hydroxyl group, that is also on the carbonyl. So we're going to need the carbonyl group on here as well. So actually the general formula of a carboxylic acid is CnH2n+1, and the whole functional group, which is the carbonyl group, the CO, and the hydroxyl group, the OH. Following the same pattern, let's draw a general displayed formula. So again, we're going to have a carbonyl group. That's the similarity between all 3, and yet this time, instead of either a hydrogen or an alkyl group, we have a hydroxyl group, and that's what makes it a carboxylic acid. So there's the functional group that I've drawn so far, and on the other side of the carbonyl carbon we're going to have any alkyl group, like so. So why don't we go ahead and draw propanoic acid. We'll draw propanoic acid, and so you can see the naming convention. for a carboxylic acid, we just take the carbon chain, in this case propane, and we're going to add the ending oic to it, and we're going to call it, in this case, propanoic acid. Okay, so prop again is 3, and so we want a carbon chain 3 long. Our functional group has to come at the end because there's 4 bonds there to the carbon, so we're going to draw a functional group in there, and we're just going to finish it off with the hydrogens on the other carbons. So that's our propanoic acid. All right, and in the same way as we did before, let's draw a diagram and then name it. Okay, so again we're going to have 3 carbon chains, 3 carbons in a chain, and yet this time we're going to have hydroxyl group, acid group. So that's the acid group on the end, but why don't we make another acid group on the other end, like so. So there's a carboxylic acid, but you notice that we've got 2 carboxylic acid groups, one on either end of the molecule. So in this case we're going to call it dioic. The ending is going to be dioic acid. And the first part of the name, as usual, comes from the number of carbons in the carbon chain. And in this case we've got 3, so it's going to be propane dioic acid. Propane dioic acid. Now notice the E when we were dealing with a single carboxylic acid functional group in the molecule, we dropped the E, but with the dioic acid then we keep the E from convention. So there we have the very basics of aldehydes, ketones and carboxylic acids. What we should move on to now is how to make them. Right, so let's start off with a primary alcohol. Let's start off with ethanol. So we're going to have 2 carbons, hydroxyl group. Let's put in oxygens, lone pairs, and complete our hydrogens. Okay, so now we have display formula of ethanol, and when we oxidize that, all right, we can summarize it. So we need an oxidizing agent. It could be sulfuric acid, could be potassium dichromate, but the mechanism in this case is not what we're interested in. We're kind of interested in the result. So what we can do is we can put an oxygen in square brackets like that to illustrate the fact that we're oxidizing it. And the product that we get with a primary alcohol, you can see a primary alcohol has just got 1 alcohol group coming off and 2 hydrogens, so it's primary alcohol. And what we're going to get is we're going to get an aldehyde. Okay, so what we've done is we've increased the number of bonds to oxygen in this oxidation process, which is one definition of oxidation. So we're going to have hydrogen, and we're going to have also the rest, the little methyl group is still there. Okay, so that is what happens when we oxidize it in the first stage. We're also going to have a water molecule that's going to drop out to balance the equation. So like I said, one of the ways of determining whether this is oxidation or not is to look at your alpha carbon. Here's your alpha carbon. And on the right hand side, that's still our alpha carbon, and you can see how many bonds to oxygen there are, and the bonds to oxygen has increased in this reaction. So that's one way of looking at it being oxidation. Let's do the other way, which is to count the oxidation state of that alpha carbon. So we're going to first of all draw in our electrons that are in these covalent bonds. Okay, so and from electron transfer theory, we know that carbon is going to lose the electron to oxygen because oxygen is more electronegative. Carbon and carbon are going to share one each, but carbon is more electronegative than hydrogen, so it's going to take it's going to take all of those electrons there. All right, so it started off with 4 valence electron when it was an atom, and we count here in the purple line. We can count 1, 2, 3, 4, 5 electrons. So we have an oxidation state of -1 to start with. Let's do the same thing here. So let's draw in our electrons in these covalent bonds, and let's then assign them to either carbon, oxygen, or hydrogen. So carbon-carbon is a tie. Carbon-hydrogen, carbon gets. Carbon-oxygen, oxygen gets. All right, so that's what we see there. And in this case, we've got 4 to start with again. And inside there, we've got 3. So we've got an oxidation state of +1. All right, so we see that the oxidation number has gone from -1 to +1, which is an increase of 2 as it happens. Increase in oxidation number means oxidation, of course. Okay, so what we could do if we wanted an aldehyde, because we've made an aldehyde there, what we could do is we could take that aldehyde out, and if we wanted to do that, we would use this distillation apparatus. Right, and I'm going to come back to describe that in a minute. Because what actually happens if we were to leave it without distilling it is that we would get a further reaction. We get more oxidation going on, especially if we use a stronger oxidizing agent like potassium dichromate. So when we get further oxidation, what do we get? Let's draw it out. We get a carboxylic acid. All right, so our alpha carbon is still bonded to our oxygen with a double bond, but this time we've added another oxygen because we've added a hydroxyl group there, and the methyl group is the same. So that's what we get when we further oxidize it. Now you can see in this case, with this carboxylic acid, we've got 3 bonds to oxygen. All right, so that's one way of knowing that this is another oxidation reaction. But just like we did before, let's draw in our electrons in all these bonds, and then count them up. Okay, so there's the electrons we're interested in here. Let's carbon-carbon's a tie, carbon-oxygen, and carbon-oxygen's going to lose that one as well. So it's only got 1 electron there, so it started off with its 4, and it's got 1 left. So that's a +3 oxidation state. So again, further oxidation by 2 electrons. So that's both ways of looking at oxidation. And why don't we mention some oxidizing agents? We could use potassium dichromate, and this is actually potassium dichromate, so chrome 2O7. That's potassium dichromate. It in this compound, the chromium has an oxidation state of +7, and when it's +7, it has this orange color. And then when it's an oxidizing agent, so it itself gets reduced, right? And so when it gets reduced, the chromium has an oxidation state of +3, and when it's +3, it's this greeny color. And so we can see that oxidation is happening because we can see this color change. We know that oxidation is happening to first the alcohol and then the aldehyde, because although we can't see the color change there from the alcohol to the aldehyde, we can see the color change in what's getting reduced, which is this chromium going from yellow to green. You could alternatively use sulfuric acid. So let's put H2SO4 in here, which might be commonly used if you just wanted to take it to an aldehyde. If you wanted to take it all the way to your carboxylic acid, then you would use this potassium or sodium, let's call it potassium dichromate. You would use that oxidizing agent there if you were interested in making or synthesizing the carboxylic acid. So let's just name all these. We've got ethanol to start with. We've made ethanol, and we've made ethanoic acid. So let's talk a little bit about the synthesis mechanisms. I mentioned earlier distillation. We've also got reflux equipment here. I'm going to explain that as well. Let's say you were interested in making the aldehyde, in this case ethanol. What you would notice happening is that as soon as you've made the ethanol, it itself gets further oxidized into ethanoic acid, which is not what you want if you're interested in the aldehyde, in which case you would want to extract it from the reaction mixture as it reacted, and you would do that by distillation, because the boiling point of ethanol would be the lowest of any of the reactants and products that are in the reaction mixture. So this would be the lowest boiling point, and so this reaction mixture would have your alcohol in there, would have your aldehyde in there that you're making, and also your oxidizing agent. And so what would happen is your aldehyde would evaporate off and would be condensed, and you would collect it in your container for condensing it. And so as it evaporated off, as it was made, the equilibrium mixture, because both of these are really equilibrium reactions, yeah, as you made some ethanol, you would encourage more ethanol to be made into ethanol. So distillation is the process that you're going to use to, let's write it in here, to make your aldehyde. If instead you wanted the reaction to go all the way to ethanoic acid, you would use a reflux operation instead, and this picture on the right shows a reflux operation, so it looks quite similar. And yet the condensing tube is connected such that what we're going to do is we're going to condense the aldehyde such that it condenses and drops back into the reaction mixture. So this is the reaction mixture. You can actually see it. It's just starting its reaction because it's still that orangey yellow color of potassium dichromate. And as it reacts, you would get your ethanol being made, and as it's made, it would evaporate, but the condensation jacket there would condense it and have it drip back into the reaction mixture so that it can be further oxidized to our carboxylic acid. So the last thing for us to do is just to label this reaction as happening under reflux and higher temperatures. The reflux allows you to operate the reaction at higher temperatures to make the oxidation a bit more aggressive. So let's move on to look at the oxidation of secondary alcohols, and again we're going to use potassium dichromate as the oxidizing agent. So that's what's going to provide our oxygen. We're going to put it like this in our equation, and it also happens under reflux, right, in acid conditions. Okay, and here's our reflux apparatus here. If you remember, anything that evaporates is condensed and drops back down into the reaction mixture to react further, and also it allows us to operate the reaction at a higher temperature than without the reflux operation. Okay, so let's have a look at an equation. So let's start off with propantuol as a secondary alcohol. Right, so we're going to have prop is 3 carbons. Propantuol means our hydroxyl group is of our middle carbon, like so, and the other carbons are just going to have normal hydrogens on them, like so. So this is our secondary alcohol. So it still has, all right, let me change colour a little bit to green. It still has a hydrogen, all right, on the alpha carbon, on the carbon that is attached to the hydroxyl group, and that is what is required to allow the oxidation reaction to happen. If you remember, in the primary alcohol reaction we had 2 hydrogens attached to the alpha carbon, and that's how we got the 2-step oxidation reaction. First of all to the aldehyde, secondly to the carboxylic acid. In this case we've still got a hydrogen, but we're only going to go one step because we've only got one hydrogen to lose. Okay, so let's add our oxygen from our oxidizing agent, and let's see what we get. Okay, we're still going to have our carbonyl group, but in this case, once we've increased our bonds to oxygen, which is what's going to happen in this oxidation reaction, we've got our methyl group off one side and we've got our methyl group off the other side, and now the molecule is complete. You can see this alpha carbon here in the middle has got its 4 bonds now because it's now got 2 bonds to the oxygen. Okay, so this is a ketone, this is propanone. Whereas we started with propantuol. And the key thing to notice is that there's now no more hydrogens on our alpha carbon. This is our alpha carbon here, as you'll know by now. It's our alpha carbon there, and in order for another oxidation step to happen, we need to have another hydrogen to lose, and we don't have another hydrogen to lose. We're not going to be able to lose either of those methyl groups, and so this is where the reaction stops. All right, so that's the difference between primary and secondary alcohols. Secondary alcohols have one step of the oxidation reaction and they turn into ketones, whereas you remember in primary alcohols, first of all, the primary alcohol turns into an aldehyde when it loses its first hydrogen, alpha hydrogen, and then there's another step because there's another hydrogen to lose, and that takes it further to a carboxylic acid. But this is where, for secondary alcohols, this is where the reaction stops. I'll leave you to count the oxidation numbers of the alpha carbons in both cases if you want to confirm that oxidations happened there. Otherwise, let's move on to tertiary alcohols. All right, so oxidation of tertiary alcohols, we can deal with this quickly because let's just draw a tertiary alcohol. And let's draw a terbutanol. I won't draw my hydrogens, my H's in. You know they're on the end of these bonds. So now you know there are no, this is our alpha hydrogen here, and there are no hydrogens connected to that alpha hydrogen. So we're not going to oxidize. So let's just write it like this to help you remember. Okay, let's draw a big black cross through there, so help you remember that tertiary alcohols do not take part in oxidation reactions in the same way, and so if they were in with potassium dichromate, the orange colour would remain, and that's how you would identify a tertiary alcohol. If you knew what you had was an alcohol but you didn't know whether it was primary, secondary or tertiary, you could oxidize it with potassium dichromate, and the first two, the primary alcohol and the secondary alcohol, would reduce the dichromate to the green colour, but the tertiary alcohol would not, it would remain orange. The only way to oxidize a tertiary alcohol would be to burn them in oxygen. Okay, moving on to testing for aldehydes and ketones, and there's 3 ways that we can distinguish between aldehydes and ketones. There's toluenes, there's benedicts, and there's phthalings. Okay, so I've got a picture here of what's purporting to be a silver mirror. So let's illustrate this as toluenes test, and we'll talk about that in a minute. And let's talk about phthalings as well, and this is a little diagram that's going to illustrate phthalings. Use of phthalings solution to distinguish between aldehydes and ketones. And the main thing to remember is that aldehydes react with either toluenes or phthalings or benedicts. Let's put benedicts in here and brackets because it's very similar to phthalings. So aldehydes react with either toluenes, valence, or benzylics, but ketones don't. So they see no change with ketones. And that's how you would know it was a ketone. Okay, so let's talk about the toluenes reaction first. And we make toluenes by mixing aqueous ammonia with silver nitrate. And so you get a silver ammonia complex. It's a diamine, and the important thing is that you've got silver 1+ ions floating around. And when you react those silver 1+ ions, so why don't we just do the reaction? When we react those silver 1+ ions with an aldehyde, let's draw our little aldehyde here. When you react those, you need a bit of water as well to balance the equation. And when we do that little reaction, we're going to have the silver ions being reduced to silver atoms, which stick to the edge of the test tube and give you a mirror effect. And as they get reduced, then the aldehyde gets oxidized, and we know when an aldehyde gets oxidized, it's going to make a carboxylic acid, like so. And to balance it, we just need 2 of those because we're going to make 2 silver atoms. All right, and we'll make a bit of hydrogen ion, a bit of acid as well as we do it. So that's the reaction that happens. So you're going to make, I should have put a 2 in there, then I didn't need to write it there. So that's the reaction that happens. So silver 1+ ions are going to get reduced to silver atoms as your aldehyde is oxidized to your carboxylic acid. And you can see the silver. And that happens with aldehydes, but it doesn't happen with ketones. Okay, so let's draw a little dividing line here and switch over to valence. Now, valence is all about copper, the blue copper color. The blue color comes from copper ions. And valence is a copper 2+ ammonia water complex, but again, we can summarize valence solution by being a provider of copper 2+ ions. Okay, so let's write our copper 2+ up here, and we're going to react that with our aldehyde again. So let's use the same aldehyde, acetaldehyde. So we're going to, and let's balance it as we go along. So we're going to need 2 water molecules as well. All right, so we've got copper 2+, which is blue, and going to do a very similar reaction. The copper 2+ is going to get oxidized to copper 1+, and that copper 1+ is going to be in copper oxide, and that copper oxide is that reddy brown color, and that's a precipitate. And we get that, and in the same way, our acetaldehyde is oxidized to our carboxylic acid, in this case ethanol, and we get some hydrogen ions coming off as well. So that's the reaction that happens with valence solution. Again, you've got copper 2+ ions being reduced to copper 1+ ions, and the color change that happens in that reaction illustrates that it's an aldehyde that's doing the reducing and getting oxidized in the process. But with ketones, that doesn't happen. Very quickly, we'll just review that we've done all our learning objectives. Did we understand what aldehydes, ketones, carboxylic acids are? Yes, I think we did. We looked at primary alcohols being oxidized in 2 steps. We looked at secondary alcohols being reduced, oxidized in 1 step, just a ketone. No further because it's only 1 hydrogen to get rid of, and oxidation of tertiary alcohols doesn't happen because no hydrogens attached to our alpha carbon, and the toluenes and valence solution tests for aldehydes versus ketones. Aldehydes react, make a change, ketones don't. Okay, so there we have it. I hope that's been clear.